Yeah, and so before I get started, just to check with you guys if the audio and the video work. Let me know if you can hear me and see my screen. Okay, awesome. Okay, thank you so much. Thanks everyone for taking time joining us for the Kaggle NanoCast week 4. Yeah, so I think so last week we skipped the class because of the family day long weekend, and I'm super glad to see you guys again. For this week, so we'll be talking about the model ensemble and a few of the tricks that are popular on Kaggle, and I believe, and I cherry picked those tricks and believe that they can be used as well for real world applications. So let's get started. So what does the model ensemble mean? So I would like to use the statistic giant George Box's quote is to explain that. So essentially, he said, essentially, all models are wrong, but some are useful. So what does that mean? So my takeaway is that, so once a model, regardless of how effective or how sophisticated, how powerful it is, once the model was selected and trained with a specific version of the data, so the angle we use the model to observe the problem is fixed, and in the meantime, so when the model learned the data, then the information from the data, so it also learns the noises from the data. So regardless of how good the model is, so it always comes with information as well as noises. So how can we resolve the problem, and how can we address the problem? So naturally and intuitively, we would imagine that we would have to imagine that. So let's say instead of using a single model, can we use a multiple model and put them together to create some synergy out of those models? So to answer the questions, we need to, let's first of all take a little bit, go back a little bit to take a look at the bias-variance trade-off diagram we discussed last time. So just a quick recap on the bias-variance trade-off. For bias, you can think it as the errors on training data set. And the variance means the errors on the test data set, right? So, and the more complex or the more stronger the model is, so naturally the bias will decrease. But in the meantime, so the variance may increase. So there's a certain point of time, so we would end up with so the good balance between the bias and the variance. And this is what we are trying to do when we train a model, to control, in summary, to control the balance between bias and the variance. We can do a few things. First of all, we can use the recognizations to penalize the models. By penalizing, I mean, so to make the model simpler, include something that can, so to control the model, to make it less complicated. So in this way, we can decrease the bias and reduce the model's complexity. Sorry, I saw there's a problem. The question, can you explain the model variance a bit? So yeah, there's a question from Alpha. Okay, so the bias, let's say we train a model, right? We train a model, and specifically, let's say we're using decision tree, we are training a decision tree model. So when from the left, if you take a look at diagram from the on the bottom of the diagram, and from left hand side to the right hand side, we see the model decision tree becomes more and more complex, right? So from one layer to two layers and multiple layers, right? And when the decision tree grows bigger and bigger, so it becomes more complex, right? And it means that so it can learn the data better. But what would happen is so let's say, imagine the model, the decision tree keep growing, and we may end up with one example on a leaf node of the decision tree, right? It means, so what does that mean? So the decision tree is able to classify the data perfectly. So it makes 100%, it has 100% accuracy on the training data. Then the training error is 0, which is the bias, right? But in the meantime, if we use this model to make predictions on future data or on same data, so it may, and it's not hard to imagine, so the error could be very, very large, just because it learns too much from the training data. And the variance or the testing error will become very large. So that's what we mean by variance. So you can the simple way to think of it is you can think it as the error on the testing data, or the data we are not the data that is not seen by the model. So what we are trying to do is to find a good point to control the complexity of the model, to make it, again, not too simple, which means so it learns too little, or not too complicated, which means it learns too much from the training data. So we want to have a good balance between the bias and the variance. Okay. Other questions on this point? Okay, so as I mentioned, so the one way we can do is to add recognizations. For instance, L1, L2 recognition for linear regression, or method depth, leaf nodes, those kind of things for decision tree. And so this is a very common way to control the bias variance trade-off. Another two ways from the multi-ensemble point perspective is it's called bagging and boosting. So let's start from the averaging. Instead of talking about the bagging, let's probably first start off with the averaging. So a very simple way to reduce the variance is let's say we train multiple models and simply average the prediction from those models, and we end up this way we can reduce the variance, and in the meantime we can return the same level of bias. Again, so in other words, we would like to train some strong models, and in the meantime we probably would encourage model to learn a little bit too much about it, or go off it a little bit about little bit. But in the meantime, so we can, in this way, we can decrease the bias. But in the meantime, by averaging the predictions, we can effectively decrease the variance. This is a very effective way to reduce the variance, but in the meantime, keep the same to retain the same level of bias. So typically, so it's very hard to train multiple models at the same time, right? So, and it's hard to maintain each model independent to each other. So one way to address that is that we can train the model we can use the same algorithm to train the same algorithm many times, but with a different version of the data. And by different version of the data, What I mean is that so we can do a sort of stochastic resampling to randomly sample some certain a portion of the data out of the original training data and train the model, train the algorithm many times with the stochastic sample data. So this way we can effectively increase the independence of each model, of each trained model. And by averaging those independent models prediction, we can effectively decrease the variance. So this is one way to make another way to make a good balance between bias and variance. And the third way is that if we don't want to, instead of using a strong models with lower bias, we can train many models, and each model comes with no bias. Or in other words, we can train some small model, a less complicated model, and every model we don't want them to have no bias. And in other words, so we want them to be a little bit conservative. And in this way, we can keep the variance very low, right? We can keep the variance low, but every time so the way to improve that, so we keep training it again and then again. So every time it tries to improve on top of the models previously. To make improvements on previous models. So this is another way we typically call it boosting. And don't get confused by those. Don't get confused by those terminology quite a bit, because so our focus today is not to explain so what is the difference between bagging and bagging boosting. So basically, what we are trying to do is to explain why model ensemble is effective. And most of the time we will be focused on most likely we will be focused on the bagging or averaging only. So we won't be talking about too much about the boosting technique. But so next thing is, so I would like to take a little bit close look at from the mathematical point of view to explain why. So averaging the predictions from the multiple models can effectively reduce the variance. So let's assume so we train the n models, and the y hat I, y hat n to y hat n be the predictions from n models, and assume they are independent and consistently distributed. So therefore, we can easily calculate that. So the variance of those predictions could be the variance of each model and divided by n. So that's based on the assumption that those models are IID, but that's not the case. That could hardly be the case for real world scenarios, right? Because so the model can not be totally independent to each other, and they most likely they would have some sort of a correlation to each other because they are trained using the not exactly the same version of the data, but very similar set of data and the algorithm. So each algorithm could have some similarities. So therefore, it's very hard to assume so all the models are independent to each other. So if we include the correlation of each model and into the formula, so we can convert it to in the form in the below. So essentially, so the form would be largely depend on the correlation P of each model. Or again, so I don't want to confuse you guys, but so if you get confused by the formula, don't worry about that. So, but the point I'm trying to make is that, so first of all, averaging the predictions from multiple models can reduce the variance. That's the first thing. The second point is that, so how effectively we can reduce the variance depends on the correlation between each model. Or in other words, so we would like to have the models for ensemble to be independent as possible to each other. And so, and to simplify the statement, so to simplify the statement, we would like to train the models in a way that they have the biggest diversity. So in that way, so we can effectively reduce the variance of the multiple models. I'll explain more so in the time, so we can take a closer look at it. What does that mean exactly? So basically, what to consider for model ensemble. Here are a few things we need to consider when we construct the multiple models for model ensemble. First of all, we'd like to diversify algorithms. That was from the the conclusion from the last slide. So if the correlation between the models become larger, so the larger the correlations of each model, the more effective the model ensemble, the variance we can reduce. So therefore, so when we are preparing the models for ensemble, we'd like to use different kinds of models and trying to make them as independent as possible. So in my experience, so GPT algorithms such as XGBoost and LightGBM, along with the neural network models, have been found to be the best, the most effective combinations for pretty much all the Kaggle computations. So, and essentially, if you could train a good GPT model as well as and coupled with a good neural network model, so it would be very promising that most likely, so they will by averaging the result from the two models, so you would end up with a promising result. And the random forest actually boost with the linear booster are good complements to the the solution of an ensemble. And sometimes I also seeing factor machine and the variants of factor machines so work very well for click-through rate computation problems, and as well as for the computation, so where we see a lot of categorical features. So GPT and the neural network are the best combination for pretty much all the computations. But if we would like to make it better, we can include random forest, actuates, XGBoost with the linear boosters, or FFM, PeopFM, those kind of algorithms to the combination of to your solution of ensemble. So these are the effective choices for considering what models to include for your ensemble. So that's how we want to diversify algorithm. And the second thing is we would like to diversify training data or even test the data. Random forest, this was because we would like to make the algorithm, even for the same algorithm, if we train the models with using the same algorithm, we'd like to make them a little bit different from each other. And the quickest way to do that is instead of training the models, always using the same version of the data. So we can train the same model with a different version of the data. So random forest and GPT, this algorithm enforce this process by introducing two parameters to control that, which we've briefly discussed in last week's session. They both have a parameter called condomism by tree, which controls how much percentage of features you would like to include for training whenever we resample the data, and as well as another parameter called subsample, which controls how much percentage of samples we would like to include for training for each model. So those two parameters control the process of stochastic resampling. And using these two parameters turned out to be two of the most important parameters to tune with when we are tuning random forest and GBDT. Another way to control, to diversify the training and even the training data is called submodeling. So what does that mean? So imagine you're working on a housing price model for United States, right? And it's not hard to imagine that the patterns for housing price may vary from one place to another place, right? So in the Midwestern the housing price in Midwestern United States may be, so much lower than housing price in, so in New York or in San Francisco. So that means, so if we train a global model, we just recognize the variance on the housing market. So if we train a single model using all the data from everywhere, from all the United States market, it may not be the best the way to do that, right? And so instead of training a global model, so we can train some submodels. And by submodels, I mean, so we can train models by state, we train models by city, we can train models by county, and just simply averaging the predictions. And so we could end up with a better solution. So this is a simple, this sounds quite simple, but this is a very effective way of doing so. If you take a look at the Zillow, I'm not sure if you guys heard of the website of Zillow. Zillow is the biggest house listing website in the United States. It provides an estimation for every single use the house listings on the market. So the way they train the model is exactly what they discussed. So they would train the state models, several state models, and even county models, and averaging the predictions along with the global model, so to get a better prediction. So this is how, so they ensemble the models, the different models. So this is called submodeling. And another way to do that is called, technically it's called data augmentation. What does that mean? So imagine, so you're working on the image classification task, right? So, and if you would like to the classifier to be able to tell if the image is a dog or the image is a cat, right? So, but regardless of if there's a cat or dog in the image, so if we flip the image, that won't change the conclusion, right? So if you flip it up, so horizontal image horizontally, so if you wouldn't change the conclusion if whether or not it's a cat or dog, right? So, and borrowing in this way, so we can, so if we have one image with a label of a cat or dog, we can simply flip the image and include the image of the flipped image into the training set. That can increase the model's capacity and to, so to identify, so to accurately classified image regardless, so that if we flicker it horizontally or vertically. So, and there are quite a few techniques we can use for data augmentation. So, but this is not the focus of today's class. So what I'm trying to say is that data augmentation is one of the ways to improve to diversify the training data. But there's another way, and that's another trick. So people that has not been aware by many people. So it's called a TTA, test time augmentation. It's pretty much like the data augmentation we talked about. But typically, when we are talking about the data augmentation, we're talking about so how to enhance or augment the data to increase the diversity of the training data. But in the meantime, so we can also do the augmentation on the test data. What does that mean is so if we were to make predictions on an image to tell whether or not to tell if it's a dog or cat, so we can make a prediction on the original image, right? And then we can flip the image and make another prediction to see if the conclusion changed. And if we end up with a different, probability of being for the image to be a cat or dog, we would just simply average the probability. That will give us a more stable, almost smoother predictions on the predictions. And typically that would be more accurate. That will increase the model's accuracy as well. So this is called the TTA, test time augmentation. You would see it, quite often for in Kaggle computations. The last thing to consider for model ensemble is to diversify training parameters. Even this is still effective, but that will give you a very marginal improvements. So if I have to do, to prioritize those three tasks, I would put it diversify the algorithm first, and then training data. And I would do the training parameter diversify the last, because so again, so it's still effective, but the improvements is marginal. So what it does is so instead of using same parameters to train the model, because if we use the same parameters to train model and use the same seed and the train model with the same version of the data, so it will be exactly the same as others, right? So, and if we just tweak the parameters a little bit and tweak parameters a little bit, so we may end up with so the models with less correlation. That in turn will give us some improvements on the model from model ensemble perspective. So questions? Okay. So let's see. For this slide, I'd like to talk about the techniques that can be used for model ensemble. And these are some very, very fundamental basic ideas for model ensemble. It's quite simple. So we can simply average everything, or use a weighted averaging, or use a ranked averaging. So ranked averaging is something I'd like to spend a little bit of time to talk about. So it works for imbalanced binary classifications specifically. Specifically, if the problem is the problem with the model's performance is measured by RC AUC, so we can use the ranked averaging instead of the naive the simple averaging. So the ranked averaging would improve the performance, performance a little bit. So what this ranked averaging means that, so instead of you simply averaging the probability predicted by each model, we would rank the probability of each model, then averaging the result based on the ranks. There's a question from Alan. So how the submodels combine average? Yes. So the quickest way, the simplest way to do it, to combine or to ensemble the model is through averaging, right? In the previous slide, what I discussed is what to consider when we prepare the models, right? And once we prepare the multiple independent or less correlated models, and the next thing we need to think about is how can we leverage the predictions from those models, those less correlated models. So this is what we are talking about for this slide. So we can do it through averaging, by weighted averaging, or by ranked averaging, or by voted averaging. Voted averaging works when we only care about the classification outputs, but voted averaging does not work for regression problems. And the last one is the harmonic averaging. So I'm seeing it being used for regression problems where the target value is always positive. So in that case, the harmonic averaging works better than the simple averaging in some cases. So, but essentially, those are just some simple ideas. So once we train the model, once we train the different models, and how can we put them together effectively, right? So, but as you can imagine, so if you have to guess, I would say, so probably weighted averaging makes the best sense in terms of how to combine different models, right? But the challenge is there's a significant challenge here, right? So for weighted averaging, how can we determine how much weight we need to assign for each model? Then naturally, we would think, okay, so we can do some validations for each model, right? So whichever gives us the best validation accuracy, we would give it a little bit more weight, and give the less weight on the weak models, right? Which makes perfect sense. But sometimes we would need work on not only just a handful of models. Sometimes we need to work with hundreds or even thousands of models. In that case, how can we effectively put them together will become a real challenge, right? So, but the idea, a natural idea is that, so if we go back to the the naive definition of supervised learning, which is given a set of data and along with some neighbors or targets, we can train supervised learning to learn the correlation between those variables and the target, and come up with and to let the model to learn the hidden patterns out of the data. So specifically, if we recall the definition of a logistic regression or linear regression, it's exactly the purpose of a logistic regression and on linear regression is exactly the same as what we're trying to resolve. It tries to come up with the best set of weights for each variable. So, and each variable corresponds to a model's prediction in our case. So in other words, so if we could train unsupervised learning models on top of those predictions and let the unsupervised learning model to find out the best weights, so our problem is resolved, right? I will pause here for everybody to think about that. So this is exactly what we're trying to do, right? So if instead of manually coming up with the meaningful weights for each individual models, we can. Why can't we just train a supervised learning model and to let the model to automatically learn the best and get the best weights for every single variables or every single models, base models. So this is what we are trying to do. This is another advanced techniques for model ensemble, which is called stacking. It is people sometimes call it the ultimate state of model ensemble in Kaggle, because it's quite effective, to be honest. But in the meantime, it's a little bit complicated, and it requires a lot of efforts to implement it and to to make it work. This is something we'd like to spend more time today, but just to make sure everybody understands what we're trying to do. So again, what we're trying to do is so when we already trained many models, so we call it base models. So how can we effectively put those the predictions from those base models together and to make them work effectively? This is what I'm trying to do for stacking. The idea is quite simple. So we can train a supervised model to automatically learn the hidden patterns or learn the weights for each base models. But there's if we take a close look at the process, so we would realize that there's a fundamental challenge, which is so in order for a supervised learning model to work, we need labeled data, right? We need a set of data with labels. But here we are talking about so finding the weights for predictions. But for predictions, we don't have a ground truth. We don't have a label to train with, right? Because the predictions was made on the data, we don't know the labels. We don't have labels, right? So, and our task is to find out the labels, right? But how can we, and without the labels, how can we train the model? How can we train a supervised model? So this is the fundamental challenge for stacking. And the stacking is what the stacking trying to do is to come up with the prediction on training data. So this is somehow confusing, because normally we would think, okay, by prediction, we're talking about the prediction on test data, or predictions on data that has not been seen by the model. But how can we come up with the prediction on training data? Right, this is what stacking tries to do. And to be short, the idea is borrowed from the concept of causal validation. So we can split the data in many folds, and each time we train a model with part of the data from training data set and then making predictions on the rest of the training data set. And repeat the process, we would end up with predictions, being able to make predictions on the entire training data set. So this may sound a little bit complex, but I will walk you through into the very details. So bear with me. So let's take a very simple case. So for simple ensemble, we would train 2 models, and we end up with 2 predictions. And the 2 predictions were made on top based on against the test data. And what we need to do is simply average them together. So we would end up with the prediction average, which would be our model ensemble result. So this is a very simple case to explain how so averaging works. So yeah, very simple, and everybody understands it. So we don't have to spend a lot of more time on this concept. But for stacking, it becomes much complicated. So I'll be talking about more details for the next slide. So the same here. So we have the trained data and the test data, right? So given the 2 data sets, trained data and test data, and the very first thing we'd like to do is to make splits on the trained data, right? So every time I'm using a 4-fold cross-validation to split data. So every time we would split the data in a way that 75% of the data will be used for training and 25% of the data will be used for validation, right? This is, if you're familiar with the cross-validation, this is a very simple way. This is not hard to understand. So, but how can we leverage it for stacking? So again, bear with me. I'll work you through the process. So let's say for fold 1, we use the first 70% of the data to train the model, for 1 time. And once we train the model, we get to train the model with 75% of the training data set. So we can make 2 predictions. The first prediction is on against the test data. So we would make a whole bunch of predictions on test data using the model trained with the first 70% of the data, right? This is for the first fold. And in the meantime, we can use the trained model to make predictions on the rest of the 25% of data. So we end up with the predictions on the, we end up with the predictions on the, what is that? On the 25% of the data. So we then repeat the process for another fold. In that case, we use the first 50% of the training data, and the last 25% of the data to train the model and make predictions on, so 50% to 70%, and which is again, so 25% of the training data, and to make predictions on the rest of the 25% of data. And we end up with the same, we would make predictions again for test the data and the 25% of the training data. And the repeated process again and again, right? So repeated process for 4 times, which corresponds to 4 folds. So now we have, for test the data, we have 4 predictions, 4 set of predictions. And for training data, we also have 4 set of predictions. The difference is that for test data, every time the prediction was made on the entire test data. But for training, every time we only made predictions on 25% of the training data, right? And now, so how can we combine them? So we need to do it differently. For testing data, we would simply average the predictions of the 4 sets of predictions. So we average them. So we end up with a single predictions, which is the average of the prediction from the 4 models, right? And for training, it's simple. So again, it's simple, but it's a little different. So we would stack them together vertically. So in this way, we end up with predictions, a single predictions on training data set, right? So if we think about the shape of the predictions, for this one, train M1, it has one column, and this is a vector, right? So length it's the same as the training, the number of examples for training data set, but it comes with one single column. That's the same thing for the prediction of test for model 1. So it is a single column vector, and the length corresponds to is the same as the length of test data. So therefore, we end up with 1 predictions for train data and 1 predictions for test data. 1 predictions for test data. The prediction was made by 1 model. And let's say if we would like to train another model, we train it with a different algorithm, and we repeat the process. So we end up and do it for 4 times. And for test, again, so we average a prediction. And for training data, we stack the prediction vertically. So now we have, for training data, we have 2 predictions, and each predictions was from one of the model we used to train the model, right? And for the test data, it's the same thing. We end up, we now have 2 predictions, and each prediction was from one of the models we used to train them. Okay, so now what we need to do is to horizontally stack those those set of prediction together. So now we end up with 2 data sets. The pre-train comes with 2 columns, and each columns corresponds to 1 model we used to train the data. And it's the same thing for the pre-test. It also comes with 2 columns, and each column corresponds to 1 model we used to train the data, right? Okay, so now we have 2 sets of data, pre-train and pre-test. And pre-train will be our new training data, and the pre-test will be our new test data. So the beauty of this process is that, so in doing that, we end up with a new data set. It also comes with learning the label, right? So we can simply use the same labels from the original train data set and use that labels along with the pre-train. We can then train our stacking model. So make sense? I would just pause here for a little bit moment to for everybody to read through the process and make sure you understand this process. If you have other questions, so feel free to raise your hand, and I would be more than happy to address that. Okay, there's a question. So after stack, variance will reduce. Yes, the average. No, sorry. After stack, variance will reduce. So this is another way. The variance will reduce after average, but not after H stack. By H stack, so what I'm trying to do is to come up with new sets of data that can be used to train our stacking model, which is also a supervised model. It requires labeled data. This is what we are trying to do for stacking. So the average, so I think you are talking about the different thing. Here we're not concerned about the decrease of variance. So what we're trying to do, here is to come up to train multiple models, and then using the outputs of multiple models to train our stacking models. But the challenge again is that if we train model and make predictions, we will only be making predictions on test data, and this kind of a prediction will not have labels along with it, and therefore we are not able to train a second model or stacking models on top of predictions. Right, and that's why we wanted to use the ideas of crowd validation to allow us to come up with predictions on training data, and by being able to come up with the predictions on training data, we can leverage labels from the original training data set to help us train the stacking model. So this is what stacking tries to do. Okay, any other questions?
Hi, Chris.
Yeah.
So my question is, because we're using the kind of cross validation,
yes.
we use like 85% of X train. Would that mean that with our stack model for our training sample numbers will be reduced to 85%?
Can you say it again?
So like if we're using the cross validation, say like our X train is 85% of the data samples. So in the stack model, our new trained data set will be 85% of the original data samples?
No, so it will be the same. It will have the same number of samples of the original training data set. So if you take a look at the length, right? I deliberately make the length the same as the original data set rated. Therefore, you can see so from the number of example perspective, they have the same number of examples. Because so say for the first cross validity for first fold, right? The X train has 75% of the original training data, right? And the predictions was made on the rest of 25%. And so this corresponds to here, right? So, and if we repeat the process for 4 times, so 25%, 25%, 25%, and 25%. So we end up with 100% of predictions on training data.
Oh, okay, gotcha.
And each one of the predictions is out of fold predictions, which means there's no need to be worried about the outfitting problem, because so the prediction was made on data that was not seen by the training process.
Yeah, I see. Thanks.
Yeah. Otherwise, if we train the train model on the entire training data set and then make predictions, so we are basically doing the in-fold prediction, which is a severe problem, because basically we are make prediction on the training data itself, which is incorrect. Therefore, we will have to use out of fold predictions, which means so every time we'll have to use a part of the data to train the model and then make predictions on the rest of the data. But repeating the process, we could get we could end up with 100% of predictions, which are out of fold predictions for the training data set. So this is a key idea for stacking. Okay, other questions? Okay, let's move on. So now we end up with two data sets, right? So remember that, so each data set pre-trained comes with two columns or two features, and each column or each feature corresponds to one model, right? So you can see the and it's the same thing for the pretext, and pretext comes with two features, and each feature corresponds to a model, one of the prediction from one of the models we use to train the data. So now, again, so we have two data sets, and each data set comes with two columns. And for pre-train, we also have the neighbor derived from the original trained data set, right? Now we can move forward to train our stacking model. Okay. So now we have the pre-train and the pre-test. What we need to do is we can train another supervised model, and then make predictions on the final on the pre-test, and then we end up with our final predictions. So here we are. For the example, we use two models for demonstration perspective. But you can easily imagine, instead of two, we can easily, it wouldn't take too much trouble to add so many models in between, right? So, and let's say if we trained 100 models here, so the pre-text and the pre-train will contain 100 features, right? And then the second layer model, which is the stacking model, will train on a 100 feature data sets, right? So, and then make a prediction on corresponding 100 feature data set to make our final predictions. So this is the end-to-end stacking process. So we can, for someone who, so at this point in time, some of you may have realized that. So instead of, okay, this framework is pretty resilient and scalable. So if we repeated the same process that we did for base models, and we repeat the same process for the stacking model, right? So we can easily get multiple models, right? So, and so here, so instead of using one stack model, so we can get two stack models, right? So, and then, so we can simply, of course, we can simply average the two models and predictions to come up with to calculate our final predictions, right? So, and we can also to repeat the same process here and just do the stacking again for the stacking models, and then have another layer here, then have another layer, then have a layer, right? So it's quite resilient, it's quite scalable, right? So, and regardless, and the beauty of another beauty of this framework is that it doesn't care about what the outputs in between. Say if we train a model, so remember for the 2 sigma ring top problem, right? So we see it as a classification problem. So 2 being high interest and 1 being medium interest, and 0 being no interest, right? So, and we see it as the classification problem. And in other words, we see that 3 labels, 0, 1, 2, the same, right? So the same. But naturally, so it could also become a regression model, right? So if we could accurately make prediction, so whether it's a 0 or 1 or 2, right? Because it's comparable, it's a rankable, it's an ordinal data, right? So, and which makes it also a possible candidate for regression model, right? So, and therefore, instead of using training classification models in between, we can also train the models in a remote regression way, right? So, and we can add regression models as the base models for stacking, right? So, and they are not limited to the same type of supervised learning problem. So you can extend, you can add pretty much everything that makes sense in between to to enhance, to improve the solution and the entire solution of stacking, right? So this is a very powerful, very resilient, and very effective framework for multi-ensemble. That's why it's called the ultimate state of a multi-ensemble. So here's the quick overview on the what I did for the two sigma rent-hub computation. So for that specific computation, I ended up with a few 30-ish to 50-ish base models, which is showing as the center of the diagram. But one thing I would like to emphasize, bring your attention is that, so when we constructed the base model, so come up with a base model. So keep in mind, so we would like to keep them as diversified as possible, right? So that's why I had XGBoost, like GBM in between, and as well as the neural network models, random forest models, SVM models, linear regression models, and FF models, right? So they complete to each other. So in other words, they have the biggest diversifications across between each other. So that's one thing. Another thing, remember we talked about, so train the models using different versions of data, right? Therefore, so we train the models using different, even for the same model, same algorithm, we train it differently, right? So for instance, for XGBoost, we train it, the one way to train it is to use all the numerical features along with the label encoded categorical feature, or we can train it again, but so get rid of the label encoded categorical feature, and instead we would use the one-hot encoded features, right? So therefore, we end up with training the model, training the same algorithm using different types of combination of features, right? Which also effectively increase the model's performance quite a bit. So, and for the stacking models, I also use the XGBoost and neural networks to train the as the models to train the stacking model, to train the stacking layer. So the one thing one thing I'd like to mention is that, so for the previous slide, right? So we talked about, so how to leverage the predictions out of the base model to train our the stacking model. But in fact, a better way to leverage the prediction is to stack them along with the original features. So if you take a look at here, so for the XGBoost stacking models, so I didn't only use the predictions from the base models. So I also included the original features from the original dataset, original training dataset, right? So you will see, okay, so these predictions go to the second layer of XGBoost models, but the original features also go to the XGBoost models as well. But in the meantime, so I purely only used the predictions for the neural network models for a stacking model, Reason being, the neural network models, they are they're not able to deal with the category, well, the neighbor encoded categorical features. Remember, we talked about for the first week, we discussed when we are discussing different types of encoding techniques. We said that so the neighbor encoding only works for decision tree based models, but they will not work for the linear models, including the neural network models. So that's why for the second models I do, so the second layer of the stacking models, I use the different tech strategies to select the features that will be used for the stacking models. So by the end of the day, so the Casanova stacking is just a black box which automatically automates the stacking process on the fly. So you can think it as a black model, so which does some complex things. But by the end of the day, so I simply average the three outputs from the three stacking models and just average them and create my final submission. So this is the final solution for the 2 sigma ring hub competition. In real world, I would never imagine. So we have to do something like that, something crazy like that. It's just too complicated to implement, and but engineering perspective, it will be a nightmare for for the developers and the engineers. So, but some kind of simple stacking, for instance, if we train multiple models here and just for the second layer, so instead of training another model, maybe we can just simply average it out. So that probably not a bad solution as well. But if we are looking for the best result, so this is something to go with. So to be honest, so nowadays, if you would like to win Kaggle competition, this is something you probably have to end up with. So maybe not as complicated as this one, but maybe more complicated depending on how the problem is and how complex the problem is and how much efforts, how much time you have. So, but again, so this is an example to demonstrate so the end stacking process. Next, I will be talking. Okay. There's a question. So there's a question from Alan. In level 1, by training process, we got parameters. In level 2, by stacking model, we average the parameter. No, we don't. There's nothing to do with the parameters. So for level 1, we got predictions. We got predictions on the data, and in level 2, we average the predictions. So here we are talking about the predictions and not talking about there's nothing to do with the parameters. So does that make sense? Okay, if you have any questions, I think we still have some time. So after the at the end of the process, so maybe we can discuss more questions later. But now let's move on. Do we need this question from Diana? Do we need all 5 models in level 1? No, not necessarily. So it depends most of the time. So I would say even you train 5 or few of the light GBM models or XGBoost models, so using different parameters, so you would end up with a decent result. Or if you want to do it better, so train several like GBM models, so several XGBoost models, as well as some neural network models. That's probably the best thing you can do. And the rest of them only give a marginal boost in my case. It's just so typically by the end of the computation period, right? So you would like to squeeze every ounce of the energy out of the of possibilities out of the data, and to make even a tiny bit improvement on the leaderboard. So, for computations, you probably want to do that, but in real world, so yeah, again, so simply train several IGBM models or XGBoost models is probably good enough. And you don't have to create a super duper stacking process like that. So probably you train several. I would say probably you want to train several XGBoost models and simply average the result is good enough. Okay, so next I'll be talking about the two very useful tricks for Kaggle computations, which I don't feel that being realized by lots of people. The first thing to do, the first trick is called adversarial validation. The purpose of this trick is to help us identify how different train data is from test data, or test data is from train data. And this is one of the most common questions whenever in practical data science, because every time that we probably been asked many times that, so if we train a model with some data we can collect up, but how can we tell in the future the distribution of the data will not change, right? So, well, to be honest, there's no way for us to tell if the distribution will change or not. But the second, instead of this is probably unrealistic, but a more practical question is to answer is that, so if we have new data to predict with, right? So how can we tell if they are of the same distribution or similar distributions as the data we train the model with, right? And it becomes particularly challenging if we are working on a data set, larger data set. By larger data set, I mean both from the number of sample perspective or number of feature perspective. In a typical scenario, we probably have to work with the thousands of features and millions of samples, right? So, and when new data comes in, so how can we tell they are still, the distribution remain the same or remain not, or remain similarly, right? So this is one of the questions we have to answer. And I talked to many of my friends in working as data scientists that they didn't seem to have a very good answer. But I think the adversarial validation is, well, it's not a perfect way, but it's probably the best way I have ever seen. The idea is quite simple. The idea is actually quite simple. So what we need to do is, so first of all, we vertically stack the train data and test the data together, right? And then we create a variable and set the value to be 1 if the samples are from training data, and 0 if the data of the samples are from test data. Then we shuffle the data, stack the data, and split the data in a way that we typically do our train test data splitting. And therefore, we end up with a new pair of data sets. One is, so we call it AV train, and then let's name it with the AV validation, right? So, and next thing to do is, so let's train a classification, binary classification against the AV train data set, and validate the results against the AV validation. And take a look at the AUC-ROC score. So if the AUC-ROC score is close to 1, what does that mean? So the model is able to perfectly differentiate the training data versus the test data, right? Make sense? Or if we see the models, the AUC-RC is close to 0.5, which means, okay, so the model, so the classification model has no clue which is from which examples are from training, the original training data set, and which examples are from the original test data set, right? In other words, so the distribution between the trained data and the test data are probably the same, right? So if the RUC, RC, AUC is close to 0.5, yeah, so yep, this is perfect. So we have the same distributions on both training and data set and test data set. But if the RC, AUC is close to 0, say 0.997, so therefore we need to pay attention on the test data, because somehow there are something in the data which makes it significantly different from the test, from the data used to train the model. And how can we tell which one we need to take a look at? Imagine again, so imagine we are working on the data set with thousands of features, right? So it would be very hard and time-consuming to visually take a look at one features at a time to find out which one, so which one is problematic, right? So and a simple way to do that, probably the quicker way to do that is just take a look at the feature importance. If you use you use the model that is able to calculate the feature importance, for instance, linear regression on XGBoost. So then you can use the feature importance to help you find out which features are problematic or potentially have something wrong within it that made the model easily to tell which one to differentiate the training and the test data set. So this is a very effective, simple but effective way to differentiate the trained data versus test data. And so at Kaggle, people use it as part of the sanity check, again, to make sure we are we understand the quality between the test training and test data. So if they are of the same the distribution, so we probably would trust our validation, local validation, more than the validation result, the scores on leaderboard. But if that's not the case, we need to be careful about the validation, because if the test data has a quite different distribution than training data, so that means that the validation that is done on the trained data is probably less trustworthy. So this is how we use the virtual validation for Kaggle computation. In more real world applications, we typically use it to monitor the new data or the data we need to predict. We need to predict. For instance, if we come up with custom churn models, right? So, and we run it on a regular basis. But when we make let's say we make prediction on a daily basis, but every day before we started running the prediction process, we probably would like to first of all check if the new data or new customers, they have the same distributions. The data won't change too much. Adversarial validation technique comes in handy, right? So, and therefore it allows us to quickly check the quality of the data. If we see, okay, so yeah, the distributions are yeah, pretty much the same. Okay, so then we would have much confidence on the prediction result, right? But if the so the adversarial models easily identifies the so the new data versus the data used to train the model to train the existing model. So we probably say, okay, so there's something wrong, there's something changed for on the new data, and we have to look into it and make sure we won't screw it up. So this is the usage of the adversarial validation on so on real world application. So questions? Okay, let's move on. Next very useful technique is called pseudo labeling at Kaggle. But it's basically the same idea as what was just released by Google Brain. So on February 11th this year, so Google Brain and Nano University just released the models trained with they call it semi-supervised learning method, and they name it with as a noisy student, and which achieved a state-of-art accuracy on the image method. This is a huge improvement, but it just used a very simple idea. And again, so this is idea, but it turned out that the same ideas, I would be conservative, the same idea, because there are some minor differences between the two techniques, but essentially the ideas are pretty much the identical. So yeah, I would just use the name of the interchangeably use the terminology pseudo labeling and the semi-supervised learning interchangeably for this session. But the whole idea, the idea of pseudo labeling has been used by Kagglers for quite a while, at least for the past 2 years, if I recall it correctly, and it has helped Kagglers to win quite a few competitions as well. For instance, the Santander customer transaction prediction. I had a gold medal in that competition, but the champion for that competition actually used the pseudo labeling to make a tiny improvement, which helped them to stand out. And as well as instant gratification, so which is another computation on Kaggle. So again, so the idea is very straightforward and simple, but effective. So what we need to do is, so first of all, we teach a model on labeled data, which is our training data set, right? So, and then use the teacher model to generate pseudo labels on labeled data. So this may sound a little bit weird, but let's say, so we train a model, and then we make prediction on the test data in a context of Kaggle computation. So, and out of the predictions on the entire test data, right? So, and typically, so if we are working on a classification problem, we end up with the outputs probability for each class, right? So, and then we would choose those predictions with the highest confidence or highest probability. Say if we can define a threshold to say, okay, so anything greater than 0.99, we see it as a confident, the labels as confident, right? So, and then we may end up with 1% of the tested data being labeled as a high confidence, right? So then we append those labeled data from test, and then append them to the original training data set, and then train a student model on the combined data set, so which consists of both the training data and the super labeled high confidence data from tested data sets, and then make predictions on the rest of the unlabeled data, and then repeat the process again and then again. So yeah, so this is what Google called noisy student. Sounds quite simple, but very, very effective, very effective. And again, so this is particularly helpful when we are working with small set of we are working with a limited number of labeled data, because the acquisition of labels is expensive. So there, imagine, so if we are working on the pipeline or incident problem, so you don't want to create more incidents. You don't want to increase the labeled data to acquire more data by increasing the incidence, right? That doesn't make sense. So, but what if we can acquire more labeled data, right? So this is something to go. This is something to go to use the noisy student or the pseudo labeling or semi-supervised learning schema to increase to enhance our data set. So that's pretty much all I have today. So in the meantime, so I do have a again. So I do have a notebook to demonstrate the stacking process. But while I was pulling out the notebook, so if you guys have any questions, so please visit through the conversation, and I would love to address that. But in the meantime, let me just pull out my notebook. Oh shoot! I don't think I have that on this computer. Bear with me for a few seconds. Let me quickly grab that. And to be honest, the stacking process we talked about today it's a little bit more complicated, and I find it's challenging to explain this concept to people whenever we try that. So hopefully I didn't do a bad job on that today. But again, so if you have any questions, yeah, feel free to raise it. Okay, I think I have that. Not really. Thank you for your patience. Okay. All right, can you see my screen? Hi everyone, can you see my screen with Jupyter Notebook? Hello? Anyone here?
Yes, we can see you.
Yes.
Okay, all right, thanks. Okay, so this again, so if you're familiar with
you had a chance to run the notebook. So we sent out the previous time for the previous sessions. So this is no different. So we, until the stacking part, they're identical, they're exactly the same as what we sent out the last time. And out of the way from the stacking, so here's the stack process. So you can, yeah, I won't spend too much time on the displaying the code, but you feel free to take a closer look at the code and make sure you understood the process. But here's this is the heavy lifting that does the stacking job. And here, so I would say I did a little bit trick. Remember, here's a trick. Remember we did the automatically tuning last time by using Bayesian optimization, right? So, and then we end up with, we used the best tuned parameters, set of parameters to train our final model, right? But this time, so one of the questions you may ask is, you may wonder is that, is it true that the best parameters will always perform the best? It's probably true. It's probably not true, right? Because there are some noises as well. So then instead of using the single best model or best set of parameters, we can use let's say the top 5 set of parameters to retrain the model, to train 5 XGBoost light GBM model, right? To train 5 light GBM models using the top 5 parameters from what we did for automatic tuning. So therefore, we can train 5 models using the stacking schema, and then we can simply we did it in different ways. So first of all, we can do it by simply averaging the out-of-fold predictions, or we can use a neural network model to train as a stacking model to train on the predictions only, or we can train a light GBM model with out-of-fold out-of-fold predictions from level 1 models, as well as the original raw features. So, and then we can just combine all the different things together to create our final submission. So if you followed all the process, so you would expect to see, so this process would give you top 1% of the will make you rank would have to rank you with the top 20 top 20 or top 1% on this computation. So this is pretty much what I have today. So you feel free to check it out, the code, and run it, and try to make your own submissions to see how that works. Okay, so yeah, that's all I have today. Yeah, again, so I didn't ask for any questions, and but if there's no questions, yeah, let's finish up today's session. Okay, all right, thank you so much again. So let's just wrap up today's session, and for next week, actually next week is if you missed the previous sessions, so that's totally fine, because there are some of the sessions, particularly for today's ones, so it's probably too technical and less interesting, but I would highly recommend the next week sessions if you could make it, because for next week I'll be talking about 2 very interesting cases. So one is the Santander customer prediction computation, which is the biggest computation Kaggle in Kaggle's history. So more than 10,000 participants in the competition, and I was fortunate enough to win a gold medal on that computation. I would like to share my experience with you guys. So that's one computation, and another computation is called arbiter demand prediction, something like that. So the reason it's I wanted to recommend it is because it also comes with, it's pretty much like what we have seen for the 2 sigma random hub computation, because it also comes with different all sorts of features: a category feature, numeric feature, datetime feature, geolocation feature, and image feature and text feature. But instead of using so feature engineering and feature engineering and attributes and Ligerian to resolve problems, so I actually created a very giant neural network with the different branches to take care of each type of different types of features individually, and then combine them together. So this is something really, really exciting, and I would encourage you to take if you can make it. So I would encourage you to participate in the next week's session. So okay, yeah, that's all. So I'm looking forward to seeing you guys next week, and yeah, have a nice weekend. We'll see you next week. Bye bye.